Hello, my name is Maoxuan Hu. The paper I'm gonna share with you is Search-Based Testing for Scratch Programs. Scratch is a block-based programming environment foster engagement with computer programming and are used by millions of young learners. Scratch allows learners to quickly create entertaining programs and games, while eliminating syntactical program errors that could interfere with progress. However, functional programming errors may still lead to incorrect programs, and learners and their teachers need to identify and understand those errors. This is currently an entirely manual process. In this situation, we have Whisker. Whisker provides automated and property-based testing functionality for Scratch programs. Whisker tests interact with Scratch programs through the user interface, for example, by providing key presses and mouse clicks as inputs. In Whisker, these inputs have to be scripted by a tester or can be generated randomly. The paper casts the problem of generating Whisker tests as such problem. While the visual representation ensures that statements can only be assembled in syntactically valid ways, achieving desired functionality can nevertheless be challenging. Testing, debugging, and fixing programs can challenge learners, as well as educators who may aim to support or assist them. In regular programming, this support is often provided by dynamic analysis. Given a test suite, one can check the runtime properties of a program, determine whether functionality is satisfied, and locate possible causes of failures. However, test suites for Scratch programs do not typically exist. In Whisker, the inputs have to be scripted by a tester or can be generated randomly, while Scratch programs are often trivially simple. This is not always the case, thus challenging the test generator. The main contributions of this paper are as follows. 1. Cast Scratch testing as a many-objective search problem, using grammatical evolution and many-objective search. 2. Define coverage-based fitness functions and provide efficient means to evaluate fitness. 3. Illustrate the problem domain and potential of the approach using example Scratch programs. The paper encoding Scratch tests using grammatical evolution. The genotype is typically represented simply as a list of integers, which is constants. For constant C and N productions, the number R of the production rule to choose is determined as the equation 1. In order to instantiate GE, we need to define a grammar that represents these tests. A test case is a sequence of user inputs, which is UI events. Thus, the starting production for a test case of length n is given by the equation 2. User inputs can be events sent via mouse, keyboard, or microphone. Therefore, terminals in the test grammar will denote concrete mouse, keyboard, or sound events, which may be parameterized. The equation 3 defines possible inputs. The goal of the optimization is to produce a set of test cases such that each program statement is covered. Thus, there is one objective function for each program statement. Therefore, the paper used many objective sorting algorithm, MOSA, which overcomes the scalability problems of traditional many objective algorithms. The initial random population evolves towards better populations through subsequent generations until a stopping condition is reached. In each generation, An offspring population of the same size is created by selecting test cases from the parent population and modifying them using crossover and mutation. For this, rank selection is used, which gives better test case a higher probability of being selected. The fitness function for a given target statement is encoded using the traditional combination of approach level and branch distance. Given a test T and target statement S, the fitness function is defined as the following, where alpha denotes a normalization function in a range from 0 to 1. To illustrate the proposed approach, the paper used 3 example Scratch programs shown in the figure. They are A. Ping pong, B. Fruit catching, C. Green Your City. The figure shows the coverage over time, averaged over 30 rounds with the evolution search of the paper, and randomly generate. We can tell the figure shows that for the 3 examples, the search requires around 30 seconds until all statements are covered, while random usually takes longer. So pros and cons. The pros is the extension of the whisker test generator has demonstrated its potential on a number of example programs. The experiment shows that the performance of evolutionary search is better than the random search. And the paper overcomes some performance issues, like using Hadley's accelerated test execution. The cons is that I think user actions are not sufficiently supported. Program state is not considered. The scale of evaluation is small. That would be all. Thank you for listening.